In this class, we're going to talk about the dual simplex method. So in the previous contest, we have seen that a primal problem achieves its optimal solution if and only if its dual problem also achieves its optimal solution. In other words, our solution is a primal feasible solution as well as a dual feasible solution. The simplex method deals directly with suboptimal basic solutions and moves towards an optimal solution by striving to satisfy the optimality test. By contrast, the dual simplex method deals directly with superoptimal basic solutions and moves towards an optimal solution by striving to achieve feasibility. An important primary application of the dual simplex method is its use in conjunction with sensitivity analysis. Suppose that an optimal solution has been obtained by the simplex method, but that it becomes necessary to make minor changes in the model. If the formally optimal basic solution is no longer feasible but still satisfies the optimality test, we can immediately apply the dual simplex method and find an optimal solution. This usually leads to the new optimal solution much more quickly than it would be solving the new problem from the beginning with the simplex method. The rules for the dual simplex method are very similar to those for the simplex method. In fact, once the methods are started, the only difference between them is in the criteria used for selecting the entering and leaving basic variables and for stopping the algorithm. To start the dual simplex method for a maximization problem, we must have all the coefficients in equation 0 non-negative so that the basic solution is superoptimal. The basic solutions will be infeasible except for the last one only because some of the variables are negative. The method continues to decrease the value of the objective function, always retaining non-negative coefficients in equation 0 until all the variables are non-negative. Such a basic solution is feasible because it satisfies all the equations and is therefore optimal by the simplex method criterion of non-negative coefficients in equation 0. To start the dual simplex method, after converting any functional constraints from bigger than or equal to form to less than or equal to form, we introduce slack variables as needed to construct a set of equations describing the problem. Find the basic solution such that the coefficients in equation 0 are zeros for basic variables and non-negative for non-basic variables. Go to the feasibility test. During the feasibility test, we check to see whether all the basic variables are non-negative. If they are, then this solution is feasible and therefore optimal, so stop. Otherwise, go to an iteration. The iteration also contains 3 steps. Step 1, determine the leaving basic variable. Select the negative basic variable that has the largest absolute value. Step 2, determine the entering basic variable. Check the non-basic variables with negative coefficients in the equation containing the leaving basic variable and select the one with the smallest absolute value of the ratio of the equation 0 coefficient to the coefficient in that equation. So this can also be considered as the minimum ratio test. Step 3, determine the new basic solution starting for the current set of equations. Solve for the basic variables in terms of the non-basic variables by Gaussian elimination. Return to the feasibility test. So now with all these preliminaries ready, let's actually look at an example how to apply the dual simplex method. Consider this example of a minimization problem. First, we say, anyways, this is a linear programming problem, so let's put it in the standard form of maximization while all the inequalities are of the less than or equal to form, and then introduce the slack variables. After doing that, we're going to make our simplex tabular. Again, the tabular is as before. We have the right side, the coefficient matrix for the variables, and then the left-hand side records the basic variables. From this, we can see that in the simplex tabular, equation 1 has all the coefficients positive, so this satisfies the optimality test. However, if we look at the values of the basic variables, y5 and y6, we see that their values can be read directly from the right side, -2 and -3. They are negative. So this does not pass the non-negativity restrictions. In this case, we say the solution is superoptimal because but is not feasible because it doesn't satisfy the non-negativity condition. So in this case, we are ready to start the dual simplex method. To start the dual simplex method, as mentioned, we're going to read from the right side and then pick the negative value with the biggest absolute value. So there are two negative values here, -2, -3. We pick the one with the biggest absolute value and then circle that corresponding row. The variable corresponding to this row will be our leaving variable, y6. And then now in this row, we are going to do the minimum ratio test. Now the ratio test is a little bit different as before. What we're going to do is to pick all the negative coefficients and compare the ratio to the top row. So the top row we have 3 negative coefficients, -2, -2, and -4. Compare the ratios. 12 to 2, we only care about the absolute value, 6. 8 to 2, 4. And 12 to 4, 3. And among all these 3 ratios, again, we pick the minimum ratio. So we choose this column corresponding to y4 as our column. And then the variable corresponding to that column will simply be our entering variable. Next, after figuring out the leaving variable and the entering variable, we're going to do the Gaussian elimination so that our row vector corresponding to y4, the entering variable, will be a unique column vector, meaning that all the coefficients will be 0 except for the last one. So after doing the Gaussian elimination, we change from the original basic variables at y5, y6 to the new basic variable set y5, y4. So also keep track of y4, the basic variable on the left. And then when this is done, we obtain the new BF solution. This is not feasible anymore, but this is a solution that passed the optimality test by the first row. But on the right, we still have some negative values. Again, reading all the right-hand side and then ignore equation 0, because equation 0 gives us the value of the objective function. And then we have 2 constants here. There's one -1, -2 is negative. So we're going to pick this row, and then after picking this row, we say y5 is leaving, and then we determine the entering basic variable, y2. So we do the minimum ratio test, 6 to 2, 3, 2 to 1, 2, and then 16 to 4, 4. So this is the minimum, so this is our column, and then y2 is entering. So again, we apply the Gaussian elimination to make that column unit, while we have this value being 1 and all other values should be 0. And then we obtain the new simplex tabular. Again, from this simplex tabular, we say the first row is all non-negative, so it passed the optimality test. However, on the right, again, we have a negative value, so it's not feasible. Again, so we just apply the dual simplex method, pick this row, and then do the minimum ratio test. When we do the minimum ratio test, in this case, we can see that 2 to -1/2 ratio in absolute value is 4. And then 8 to 2, the ratio is also 4. And then 3 to -1/4, the ratio in absolute value 12. We pick the minimum ratio. However, in this case, we have 2 ratios of the same value, and they are both minimum. So in this case, similarly as we've seen earlier in the simplex method, the choice of the entering basic variable is arbitrary. We can choose y1 or we can choose y3. The optimal solution will be reached anyways. So in this case, let's choose y1 as our entering basic variable and then do another Gaussian elimination. After we calculate this tableau correctly, we can see that after this iteration, then the first row has all the coefficients non-negative. And then the right side, besides the first term, which is the value of our objective function, values for the basic variables are also positive. So in this case, the solution is feasible, they're all non-negative, and they pass the optimality test. So this is our optimal solution. Again, we can read our optimal solution directly from the table. y1, y2 equals 1/2, 1, and our objective function w is simply -14. Okay, so on the other hand, we recall that during this step, we choose y1 to be the entering basic variable, but at the same time, we say y3 also have the minimum ratio. So we can also choose y3 as the entering basic variable in the last iteration and obtain another different optimal solution. The solution is different, however, our minimum value of w will remain the same, that is 14. So next, let's summarize the difference between simplex method and the dual simplex method. First, simplex method suits to when problem has initial feasible solutions, whereas dual simplex method suits to when problem has no initial feasible solution. Second, simplex method is using the simplex method, we reach an optimal solution when equation 0 has all non-negative coefficients. While for the dual simplex method, we need to check when the right side are all non-negative. Third, the simplex method first chooses an entering basic variable, then chooses a leaving basic variable, whereas dual simplex method first chooses a leaving basic variable, then chooses an entering basic variable. Last, in the minimum ratio test, the simplex method is according to the column ratio, and the dual simplex method is according to the row ratio. We end this section with some remarks. First, the dual simplex method works when there is no initial BF solution to the primal problem, while the coefficients in equation 0 in the tableau is non-negative. If there is no initial BF solution and equation 0 contains negative values, we have to use the artificial variable techniques we introduced earlier, such as big M or two-phase methods, to solve the problem.